The night sky over southern England erupts. It is 11:47 p.m. on the 17th of February, 1944, and somewhere above the Sussex countryside, a Heinkel He-111 bomber begins its final descent. The crew haven't seen a thing. No searchlight beam has caught them, no tracer fire has arced towards their aircraft, no fighter has closed in on their tail. The pilot, perhaps 30 years old, perhaps less, has flown this route 17 times before. He knows the landmarks by their absence. The blackout transforms southern England into a void, punctuated only by the occasional careless household light or the distant glow of a factory. His navigator crouches over charts marked with their target coordinates. The wireless operator monitors German frequencies for British fighter warnings. The gunners scan darkness for threats that haven't materialized. One moment they are flying straight and level at 4,200 meters, engines throbbing, the Channel coast a dark smudge below. The bomber vibrates with the familiar rhythm of twin Yonkers Jumo engines, each one burning petrol at a rate of 340 liters per hour. The altimeter holds steady. The compass bearing is correct. Everything is proceeding according to plan. The next moment, their starboard wing simply disintegrates. Metal tears, rivets shear, aluminium skin peels away like paper. The airframe shudders. The control surfaces become useless appendages. The bomber corkscrews earthward, spinning through frozen air at terminal velocity, and somewhere in that plummeting cockpit, men are screaming questions they will never have answered. What hit them? Where did it come from? Why didn't they see it? The wreckage, scattered across 3 fields near Lewes, offers no clues. Home Guard volunteers who arrive at first light find no bullet holes. No shrapnel embedded in the fuselage, no evidence of cannon fire, just catastrophic structural failure at altitude, the kind of thing that shouldn't happen to a properly maintained aircraft on a routine bombing run. The investigation, such as it is, concludes with a shrug. Enemy aircraft destroyed. Cause unknown, case closed. This is the signature of Britain's most peculiar weapon of the Second World War, a device so secret that even today, most people have never heard of it, a weapon that destroyed enemy aircraft without ever being seen, without leaving obvious evidence, without giving its targets any warning whatsoever. It was a weapon that turned the night sky into a lethal maze of invisible sensors, waiting silently for metal wings to pass within range. By early 1944, the Luftwaffe's nocturnal campaign against Britain had evolved into something altogether more sophisticated than the massed raids of the Blitz. German bombers now operated individually or in small groups, using cloud cover and electronic countermeasures to slip through Britain's defensive screen. They flew higher, faster, and with greater tactical awareness than their predecessors. The traditional trinity of anti-aircraft defense, searchlights, heavy guns, and night fighters, was struggling to keep pace. Searchlights could be evaded. Flak was largely ineffective above 3,500 meters. Night fighters, even with rudimentary airborne radar, required visual confirmation before engaging, and on overcast nights, that confirmation never came. The statistics were stark. In January 1944 alone, German raiders managed 271 successful penetrations of British airspace, dropping ordnance on London, Bristol, and a dozen smaller cities. British guns fired an estimated 47,000 shells that month. Confirmed kills: 6. That meant roughly 7,833 rounds expended per aircraft destroyed. The tonnage of explosive being hurled skyward was impressive, certainly, but the return on investment was pitiful. Something had to change. The problem wasn't one of effort or courage. British anti-aircraft crews were among the most experienced in the world by this stage of the war, but of fundamental physics. A bomber at 4,000 meters, traveling at 400 kilometers per hour, covered the maximum effective range of a heavy anti-aircraft gun in under 90 seconds. Calculating firing solutions required predicting where the aircraft would be when the shell reached altitude, accounting for wind, air pressure, and a dozen other variables. Even with mechanical predictors, the process was maddeningly imprecise, and all of this assumed you could see the target in the first place. The solution came not from the established weapons laboratories or the great arsenals, but from a team working in near total obscurity at the telecommunications research establishment at Malvern. In late 1943, a small group of physicists and engineers began experimenting with something they called proximity fusing, though the term hardly does justice to the elegant brutality of the concept. The team was led by men whose names deserve to be better known: Dr. William Butemant, who had previously worked on radar development, and Edward Shire, an electronics specialist who understood vacuum tube design better than almost anyone in Britain. They were operating under constraints that would have defeated lesser engineers. The device they needed to create had to be small, robust, reliable, and cheap enough to manufacture by the thousands. The idea was deceptively simple. Instead of requiring a direct hit or a timed fuse, create a shell that would detonate automatically when it sensed the presence of an aircraft nearby. The execution, however, was anything but simple. Consider the engineering challenge. A conventional anti-aircraft shell is fired from a gun with a muzzle velocity of roughly 850 meters per second. The shell experiences acceleration of approximately 20,000 times the force of gravity, enough to turn most electronic components into expensive scrap metal. The shell then climbs to altitudes where temperatures drop to minus 30 degrees Celsius or lower. It must function reliably in rain, snow, and high winds, and it must do all of this whilst containing enough high explosive to damage an aircraft. The device they eventually produced was a miniaturized radar transmitter and receiver, small enough to fit inside the nose cone of a standard anti-aircraft shell, robust enough to survive the savage acceleration of being fired from a gun, and sophisticated enough to distinguish an aircraft from ground clutter, clouds, or random electronic noise. The mechanism worked on a principle borrowed from bats. The fuse continuously transmitted a radio signal on a frequency of 180 megahertz, chosen because it offered a good balance between range, component size, and resistance to atmospheric interference. When that signal reflected off a metallic object, an aircraft, the returning echo would shift slightly in frequency due to the Doppler effect. This is the same phenomenon that makes an approaching train whistle sound higher in pitch than a departing one. As the distance between shell and aircraft decreased, the frequency shift increased. When the shift reached a predetermined threshold, indicating the target was within lethal range, typically 15 to 20 meters, a tiny electronic circuit triggered the detonator. The entire process, from detecting the aircraft to firing the detonator, took approximately 3/1000ths of a second. The fuse itself was a marvel of miniaturization that would have been impossible to build even 5 years earlier. It measured just 7 centimeters in length and weighed 680 grams, roughly equivalent to 3 cricket balls. Inside its compact housing were 4 vacuum tubes, themselves specially designed to withstand the shock of firing, a small battery, capacitors, resistors, and the aerial assembly. The vacuum tubes were the critical component. Standard commercial tubes would shatter instantly under firing loads. The tubes developed for the proximity fuse used heavier filaments, reinforced glass envelopes, and specially designed internal structures that could flex slightly under acceleration without breaking. Each tube was individually tested to destruction standards that would bankrupt a commercial manufacturer. Every component had to be manufactured to tolerances measured in hundredths of a millimeter. Every solder joint had to be perfect. The battery, a tiny zinc-carbon cell, had to deliver 67 volts reliably despite temperature extremes and mechanical shock. The aerial, a simple dipole arrangement, had to be precisely tuned to the transmission frequency. A single loose connection, one poorly seated tube, one battery that failed to hold charge, and the shell would be useless, a very expensive piece of ballast that would fall back to Earth without ever fulfilling its purpose. Manufacturing took place at several locations across Britain, though the precise sites remained classified throughout the war, and some remain classified to this day. What we know is that by March 1944, production had reached approximately 1,200 units per week, each one hand-assembled by workers, often women, who had no idea what they were building. The security protocols were extraordinary. The components arrived separately from different suppliers who themselves had no knowledge of the final product. The assembly happened in isolated facilities where workers were told they were building radio components for field communications equipment. The finished fuses were tested using equipment that revealed nothing about their purpose. Even the shells that would carry them to battle were loaded at different locations. No single worker or facility saw the complete system from start to finish. This elaborate security apparatus wasn't paranoia. The proximity fuse represented such a significant technological leap that its capture by German forces would have been catastrophic. German engineers, given a working example, could have reverse-engineered the design within weeks. For this reason, the weapon was initially prohibited from use over land, where a dud round might fall into enemy hands. Only over water, where failed shells would sink beyond recovery, was deployment authorized. This restriction remained in effect until June 1944, when the strategic situation in northern France became desperate enough to risk using the fuses over land. The first operational use of British proximity-fused anti-aircraft shells occurred on the night of 12th March 1944, when batteries defending Portsmouth engaged a formation of Junkers Ju-88 bombers approaching from the Channel. The gunners, veterans of 3 years of night defense, knew their business. They tracked the incoming formation on radar, calculated firing solutions with their mechanical predictors, and opened fire at 23:17 hours precisely. But this night was different. The shells climbing into darkness carried passengers the crews knew nothing about. Gunners reported something extraordinary. Shells were detonating in the vicinity of aircraft without requiring the precision of a direct hit. Observers saw bomber formations scatter as shells burst around them with uncanny accuracy. Bombers that would normally have passed through the barrage unscathed were suddenly staggering, trailing smoke, losing altitude. One Ju-88 fell into the channel 8 kilometers south of the Isle of Wight. Another crashed near Chichester, its port engine destroyed by fragments from an explosion the crew never saw coming. A third limped back to its base in northern France, with 62 holes in its fuselage and tail section, testimony to a shell that detonated perhaps 12 meters from the aircraft. The psychological effect on German crews was immediate and profound. Flak had always been a calculated risk, something to be endured and evaded. Experienced pilots knew the patterns: climb above the ceiling of heavy guns, descend below it, use clouds for cover, vary your altitude and heading. You could see the shell bursts. You could watch the black puffs of smoke appearing at your altitude and adjust accordingly. You could take evasive action. You could climb above the effective ceiling or descend below it. But this was different. Aircraft were being damaged and destroyed by explosions that seemed to anticipate their movements, that detonated at precisely the worst possible moment, that appeared almost intelligent in their targeting. Pilots reported shells that burst directly alongside their aircraft, despite evasive maneuvers. Navigators described explosions that followed them through turns and altitude changes. The flak over England had, quite literally overnight, become far more lethal than anything they'd encountered over Berlin or Hamburg. Luftwaffe after-action reports from this period, later captured and examined by Allied intelligence, reveal a growing unease bordering on superstitious dread. Crews reported coincidental explosions, shells that burst impossibly close without warning. Some began to suspect Britain had developed a form of remote-controlled ammunition, shells that could somehow be guided onto target after firing. Others theorized about acoustic fuses triggered by engine noise or optical systems triggered by moonlight reflecting off wings. The truth that the shells were guiding themselves using miniature radar sets that would have seemed like science fiction just 5 years earlier was both more mundane and more terrifying than any theory the German crews could devise. Records from this period are frustratingly incomplete. The proximity fuse program remained highly classified long after the war ended, and detailed statistics on its effectiveness were either never compiled or have never been released. Operational reports were deliberately vague, attributing kills to improved fire control or better training rather than revealing the existence of the fuse itself. What we can piece together from fragmentary sources, gun battery logs, RAF intelligence summaries, captured German documents, suggests that by late April 1944, roughly 40% of anti-aircraft shells fired over southern England were equipped with proximity fuses. The kill rate, aircraft destroyed per round fired, improved by an estimated factor of 5. Put another way, where previously it took nearly 8,000 shells to destroy a single aircraft, proximity fuses reduced that number to fewer than 1,600. Still not efficient by modern standards, but a revolutionary improvement by the standards of 1944. If you're finding this interesting, a quick subscribe helps more than you know. The Germans, it should be noted, were working on their own proximity fuse designs. Documents recovered after the war reveal at least 3 separate programs, one run by Telefunken, another by Rheinmetall, and a third by a team at the University of Berlin. None achieved operational status. The German designs were conceptually sound, but suffered from insurmountable engineering challenges. Their vacuum tubes couldn't survive the firing shock. Their batteries couldn't deliver reliable power. Their circuits were too sensitive to temperature variations at altitude. Most critically, by late 1943, Germany simply lacked the manufacturing capacity to produce such sophisticated devices at scale. The Rheinmetall design, perhaps the most advanced, required 17 separate vacuum tubes, each one a potential point of failure. Compare this to the British 4-tube design, or the American VT fuse, which used 5. Simplicity, in this case, was not just elegant, it was essential. The Americans, meanwhile, had developed their own proximity fuse independently, the famous VT fuse that saw extensive use in the Pacific Theater.
The British and American designs shared the same fundamental principle, but differed in execution. The American version used slightly different frequencies and employed a more robust, if less sensitive, detection circuit. In direct comparison, the British fuse was marginally more accurate, but also more expensive to produce, approximately 7 pounds per unit versus 5 pounds for the American equivalent. Both were vastly more effective than anything the Axis powers fielded. What's remarkable is that despite operating independently for most of the development period, British and American teams arrived at nearly identical solutions to the same problem. When technical information was finally shared in early 1944, engineers on both sides of the Atlantic reported being uncannily similar in their approaches. The proximity fuse's impact on the strategic bombing campaign against Britain is difficult to quantify with precision, but the broad strokes are clear. German losses over southern England increased sharply from March 1944 onwards, whilst the tonnage of bombs successfully declined in inverse proportion. By May, Luftwaffe Bomber Command had effectively abandoned sustained operations over southern England during hours of darkness. The official explanation, repeated in post-war histories, emphasizes the success of RAF night fighters equipped with improved radar. This is true, but incomplete. Night fighters certainly played a role, but the unglamorous reality is that a significant portion of German bombers were being destroyed or damaged by anti-aircraft fire that, for the first time in the war, actually worked as advertised. The psychological impact extended beyond operational losses. German crews who survived encounters with proximity-fused shells reported a sense of helplessness that pure fighter opposition never inspired. Against a fighter, you could maneuver, return fire, perhaps even escape. Against shells that detonated themselves at lethal range, there was nothing to do but fly straight, hope, and pray. Morale, already strained by years of attrition, deteriorated further. The weapon's legacy extends well beyond the Second World War. Proximity fuses became standard equipment in anti-aircraft systems worldwide and eventually found applications in surface-to-air missiles, where they remain essential today. The fundamental principle, using reflected electromagnetic energy to trigger detonation at optimal range, underpins much of modern air defense. Several examples of British proximity fuses survive in museums, including specimens at the Imperial War Museum in London and the Royal Air Force Museum at Hendon. They sit in glass cases, unremarkable objects roughly the size of a torch battery, and visitors walk past them without a second glance. There's no drama to their appearance, no obvious menace. They look like what they are, electronic components from another era, vaguely quaint, certainly obsolete. But held in your hand, examined closely, they reveal something else entirely. Evidence of a moment when British engineering reached a level of sophistication that fundamentally altered the mathematics of aerial warfare. The night sky over southern England erupts, and this time we understand why. It is still 11:47 p.m. on the 17th of February 1944, but now we can see the invisible architecture of Britain's defense, radio waves spreading outward from shells climbing through darkness, searching, calculating, waiting for the return echo that signals an enemy in range. The Heinkel's starboard wing disintegrates not by chance, not by impossible luck, but because a device the size of a cricket ball, fired from a gun 6 kilometers below, sensed the bomber's presence and detonated at precisely the right moment to convert high explosive into shrapnel traveling at supersonic velocity. The crew still haven't seen a thing, and they never will. The wreckage scattered across those 3 fields near Lewes contains the evidence of their destruction, but offers no explanation they could have understood. What hit them was the future arriving ahead of schedule, a weapon that transformed anti-aircraft defense from calculated guesswork into applied physics, from hurling metal skyward in hope to delivering it with near-surgical precision. The German bombers that survived that night and the nights after carried reports back to their commanders about shells that seemed to know where they would be, about explosions that followed them through evasive maneuvers, about a defense that had suddenly, inexplicably, become lethal. They were describing technology that wouldn't become commonplace for another generation, miniaturized electronics and autonomous targeting systems that in 1944 seemed like something from the pages of science fiction. But they were real. They were British. And for a few crucial months in the spring of 1944, they made the night sky over England the most dangerous place a Luftwaffe bomber could fly. That forgotten weapon, that device most people have never heard of, that proximity fuse sitting unremarked in museum cases across Britain, destroyed German aircraft without being seen, without being understood, and without receiving the recognition it deserves. It was, in every sense that matters, the future of war arriving 3,000ths of a second at a time.